computer. All right, good afternoon. My name is Jordan Gallivan,
My name is John Phillips.
I'm Joseph Cagle.
and today we're going to be talking to you about the New York real estate price prediction application, what we're calling New York Rep. Oops.
As an introduction, as real estate prices and interest rates increase and supply decreases, finding a home has never been more difficult. New York Real Estate Price Prediction Application, or the NYREPP, simplifies this through an innovative application. NYREPP's state-of-the-art UI interfaces with a regression model to help accurately predict property values throughout New York.
A little bit of how we did this. So we're going to talk about this project in three parts. Primarily the regression model. Then we're going to talk through how we actually incorporated that into our application via a back end, and then subsequently the front end. So a quick glance at our data. So we pulled this data off of Kaggle. It was roughly about 4,000 data points, which is not nearly as much as you'd really want for a regression model, but it suited the purposes of the project. And then we wanted to jump in and see what the correlation between the data and the prediction value that we're looking for, and that is price. So as you can see in figure one, there is some correlation between position and the overall price of the property. But this really wasn't telling the full picture. So as we jump down to figure two, you can see in the scatter plot, we start to see a bit of a linear correlation between bedrooms and bathrooms and the price, but we see a really strong linear correlation in the property square footage with our price. But again, really not telling the whole picture. So as we break into our categorical variables, we can really start to see there's significant correlation between the property type as well as the sub-locality or one of the boroughs of New York City. So as we kind of turn our focus over to building the actual regression model, some of the tools we used were SCI-Kit, TensorFlow, and Keras. And we did all this through Google Colab's notebook. And you can see a link if you're interested in what the source code for that looked like on the slide. So let's jump into the actual regression model itself. So first thing we needed to do was kind of prune the data and get it ready for machine learning. First thing we noticed is there was some pretty significant outliers. There was a $2 billion property was one of the data points, and then we had a handful that were above $100 million. With the mean that we were seeing after we cleaned this up around $750,000, these values were significantly throwing off the data. So first thing we did was drop those. We also limited the string value fields that we were working with. What we found was there's a significant amount of variance in terms of addresses, just based on the actual addresses themselves, but also down to how they categorized the subunit. So is it an apartment, a unit, a number? How do they spell apartment, et cetera? So it was easier to just use the positional data of latitude and longitude. We also normalized our property types and sublocalities. The sublocalities just to the 5 boroughs within New York, and then the type itself, we kind of filtered them into these the types that you have depicted in table 1. Next up was transforming the data and preparing it for machine learning. First thing we did was run a standard scaler on the numerical values, and then we one-hot encoded our categorical values. As we'll talk about later, we tried some different methods for the categorical data and when we came to neural networks, but one-hot encoding really was the right answer for the regression models. And as you can see here, we took a very exploratory approach. We really followed the hands-on machine learning by Garan and how we stepped through this. But that was really important in terms of our own personal discovery, but also in choosing the right model. So first thing, we started with a simple linear regression. We saw some of those linear correlation on the scatter plot. But what this really showed was this isn't going to answer the mail for us. The two primary means of evaluation were our root mean squared error, which you can see is roughly equivalent to the mean. So that wasn't going to work. And then also the cross-validation scores, which are depicted in that array. Moved on to a decision tree, which looked promising with the root mean squared error. But we quickly see with the cross-validation scores is this was likely overfitting the data. So we moved on to a random forest regression, which is just a bunch of decision trees within the forest that's kind of averaged out. And what we saw with this was really promising root mean squared error and associated cross-validation scores. So we chose this model and decided to hypertune the parameters via grid search. And what that showed us is the best hyper parameters for this were going to be the largest estimators that we ran it with, which are 500, and then max features of 8. And this got our root mean squared error down to 259,000. This is ultimately the model we chose for the actual application and is what we implemented. So a quick aside on to our attempt at a neural network. We did make an effort at a neural network. Unfortunately, we were unsuccessful in really getting one to implement. First thing we tried was using an embedding layer for our categorical data. That didn't work. And then we tried one hot encoding, as you can see in figure 5. This is kind of what that looked like. Again, what we were seeing was the root mean squared error was way off, and this wasn't really a valid prediction tool for us to use. And really what it came down to was the model wasn't accounting for the weight of the categorical variables as much as they actually impacted the data, as we saw in figures 3 and 4 on those box plots. So I'll turn it over to Joseph now to continue the discussion on what we tried with the neural network and close this thing out.
Yeah, thanks. So I sort of picked up where Jordan left off. I said, is there any way to make this network better? And so I said, what happens if we just try to add more and more complexity, more and more layers, see what happens? See if it can learn that prediction function better. So I started adding just a lot of layers, nothing too fancy. On the right, you can see I've got a model that uses like 14 layers with 1,000 or 800 neurons per layer. I did some experimentation with architectures and activation functions. So I started with a just simple ReLU activation function. Adding more layers initially improved our error a little bit. And then after experimenting the leaky ReLU function with He initialization, made some more improvements. So with this model on the right, we ended up with a root mean square error of about 500,000, which is an improvement over almost 2 million before. So it's better, but it's still pretty useless, because if you're off by 500,000 predicting the price, that's not going to be very helpful. So that was training for 10 epochs. If we ramp that up to 50 epochs, yeah, same slide. After 50 epochs, the error is actually higher on the test set. And so that probably implies we've got some overfitting going on the training set. And that's kind of the nail in the coffin for this architecture, because if we're overfitting and we're getting a really bad error, that means this architecture isn't really learning the function well. Next slide. So probably the problem here is we've got these categorical variables, the one hot encoded variables, and the property type makes a really big impact on the price of the property. And so what we have effectively is sort of a piecewise function for the property value for each type of property is going to depend on different sets of factors in different ways. And so a neural network obviously can learn this function given enough complexity, but because of the discontinuity, it's going to be pretty difficult. So the solution to this, if we're using neural networks, would be either use a different architecture or perhaps split the categories into separate data sets and train separate networks for each one. Don't know if there's enough data for training separate networks with the data set that we have. But next slide. We can also try different network architectures. So there's something known as a wide and deep network, which was discussed in the hands-on machine learning book. Basically, you've got a complex, deep neural network that will learn complex patterns, but also you're going to short circuit some of the layers on the left here so that it'll also learn simpler patterns and have those affect the output more strongly. Or additionally, in a similar vein, you could have the categorical one hot encoded variables as just a separate input, and then attach those somewhere else in the model. So those are definitely some good avenues for exploration in the future. Okay, so to implement all this, we implemented a front end and a back end. So first we'll cover the back end. So basically, we took the random forest regressor model, exported that, threw it into a Flask app. So basically, we're going to take the inputs of that model. So that's going to be attributes of the property like location, square footage, all that stuff. Take all those attributes, put that through the model, and then wrap that in a web API. And then so we're going to take HTTP requests and feed the inputs through the model, then serve it back, or send a request back over the network. So we got one endpoint, basically takes all these attributes. It responds with the price. We've also got a sublocality in here that was sort of a bookkeeping item, because the sublocality actually has a decent impact on the price, but that's not immediately available from the front end controls that we have, as we'll see in a minute. So the back end checks which sublocality we're in depending on the longitude and latitude. All right, so here's the front end. So the idea with the front end was to have a map that the user could click on, such that depending on criteria that the user sets, the interface will predict the price given those attributes at the given location. So we've got a static web page built with Vite and a little bit of React in a component library. We embedded an OpenStreetMap interface, so basically just like Google Maps, but is an interactive map, and then we can draw on top of it and then hook up event listeners and things. So here's the UI. So on the first screen is on the left is the first screen that the user interacts with. So you pick your property type, set your attributes for the hypothetical property you want to estimate. Then you continue to the map, and then it brings you to the interface on the right side. So the first thing you'll notice is a lot of dots on the map. So those are a visualization of the training data set, which sort of helps you get an idea of what's going on geographically. These are filtered by the property type that the user selected. So on the control screen, if you've picked a house versus a condo, then it'll show just the houses and not the other property types. So on the right side, we've got a house. We've got the house portion of the training data set displayed. Obviously, there's a price scale color coded with a legend up there at the top. So the main component of the interface is we're going to be clicking on the map to generate prices. So the next slide. So there's an example. We've zoomed in a little bit, clicked at one spot. And then what that does is that sends a request. Go back 1 second. Yeah, so we send a request to the server with the attributes like we discussed that are displayed, for example, the ones that are displayed in the legend right now. And then the server just feeds that through the model, spits the price out, and then serves it back. And then we have our predicted price. Yeah, next slide. So the data visualization is pretty interesting. You can see all the prices for the training data set depending on the different property types, as I've said, and then we've got a few slides with different property types, and you can see how they're scattered all over the map. I think we got like one or two more. Yep. So, and with that, I'll turn it over to Jack.
In conclusion, we must be aware of overfitting models, and we must take into account the importance of exploration. And unfortunately, we require further explanation of neural networks if we wish to properly utilize those.
Thank you.
All right, so to go ahead and wrap this up, a couple things to note here. Like mentioned on the slide, some of our key takeaways are listed there, but really for version 2.0, something we'd like to incorporate is that neural network, and then start to feed the input data back into the model, and start to get a feedback loop with the user to actually evaluate the fidelity and the accuracy of the actual model itself. So overall, really effective project and for us learning this, and then really practical at the end of the day. And here are references if you are interested, and we'll go ahead and pause there for any questions. All right, none noted. Thank you all for attending. Appreciate it, and let us know via discussion if there are any other questions. Thanks.